Hey guys, how's it going? Welcome back to machine learning number 3. So for those of you who haven't went through machine learning number 1 or 2, you are going to see the link appear above you any minute now. Be sure to check out machine learning part 1, machine learning part 2, because it's going to be helpful when we go through machine learning part 3. Now in today's model, we're not going to be taking the original model and refining it any further. I'm actually going to be showing you a different way to solve the problem that we were looking to solve. So, as a refresher, we were looking at real estate data. And in this real estate data, we were looking at things like the price, the bedrooms, the bathrooms, the square feet living, square feet lot, and all that other fun stuff. And in machine learning 1 and machine learning 2, we did a whole bunch of cleansing of the data, whether it be applying cardinality, whether it be looking at different ways of reducing the data set. We originally had a root mean square error, which is what we're using to measure. So that's what we're going to call our loss function for today. We went through different mechanisms of looking at the data. And so as I scroll down here, what you're going to see is we were looking at different ways of doing this. We were looking at random forest, we were looking at linear regression, and a whole bunch of other different things. We did some modifications to the data. We appended or added some data with the existing data set. So in machine learning 2, we refined the existing model without adding any data. Rather, we took the same data frame and we just manipulated things around. We moved a few columns, deleted a few columns, and created some new data based on data that was already there. And so in that scenario, we used some regression modeling. We used a combination of different things. We used random forest. We used a few different regression mechanisms. Now, what I didn't show you last time is it's two things. I just want to walk you through. This is more of an appendix to machine learning 2. We took away any potential prices that were 2 standard deviations above the mean. What I forgot to do was take the lower bound, so I just added this in as a lower bound. When I reran the numbers, to be honest, it didn't make a big difference because most of the original outliers were on the upper bound anyways, but it's always good practice to make sure that you're taking your outliers from the top bound and the lower bound as well. And so when I reran those numbers again, random forest still came out a little bit ahead of some of the others. Now, one of the other things I've done is I've added in something called ridge regression and lasso regression, and we have not walked through these, but these are two really great algorithms that help with overfitting your model, and they walk through something called L1 and L2 regularization. We will go through that at another point in time. I wanted to save these two specific models for a different time because I want to use a new data set and I want to really explain this stuff properly to you guys. But I ran it against the ridge and I ran it against the lasso, and in this scenario random forest still came out on top, and that's partially because we did a lot of weeding of the data anyways to prevent some of the overfitting. However, when we look at future models, you'll see that in certain cases, lasso and ridge are actually very, very strong models. But I wanted to add that in here as well because as we build our next models, I will be using a different data set, but I'll use a similar concept here. So in today's lesson, what we're going to do is we're going to now solve this building a neural network. And neural networks are really interesting to work with. We're going to work with a basic neural network today. But you can use a neural network for different things. You can use it for classification, you can use it for regression. And today we're going to use it for regression. Now, typically speaking, I've always found that when I use these algorithms, I get slightly better results when I actually use a regression model rather than neural networks. I find I get really good results when I get classification or when I do classification models through neural networks. So anyways, we're going to go ahead and we're going to build a neural network from scratch. So in order to do that, we're going to import something called TensorFlow. And TensorFlow is a Google-owned neural network platform. And what it does is it provides you the means to go ahead and build some of these neural networks. Now, there's two ways to call TensorFlow. You can either call TensorFlow directly by importing the package into your own local network, or you can access it via the API. Today, we're going to do it based on importing it into my local machine. So for that reason, you would just do a pip install TensorFlow. And then you would also do pip install Keras, Keras. Keras is a library that sits on top of TensorFlow, at least that's the way I use it. And it allows you to interact with TensorFlow with a lot more ease and a lot more simplicity. And it just makes interacting with TensorFlow that much easier. So for today's session, what we're going to do is I'm going to walk you through what we're importing here. So we'll walk through this section right here. which is essentially going to be us building in this case, this is a deep learning model. Now, typically speaking, the difference between a regular neural network model and a deep learning model is a deep learning model, they say, is anything that has two or more hidden layers, or one or more hidden layers, sorry. So typically in a neural network, you'll have an incoming layer, or your activation layer, then you're going to have an outgoing layer, and that's your neural network. But if you have more than one hidden layer, that's considered a deep learning model. And what I built here is a deep learning model today. Now, the one thing I will tell you is as I'm building this model and I show you this, I have not optimized this model. I've purposely put in different things in this model to walk you through concepts, but I haven't actually optimized this model whatsoever. I'm actually using a lot of the default parameters just to show you how this is going to work. All right. Next, we're going to walk through something called dense, dropout, and activation, which I'll walk you through. These are two optimizers. One is called Atom, one is called RMS Prop. There's other ones as well, SGD, and a whole bunch of other ones as well that we'll walk through. And before I get into this, I want to go through a little bit of theory of what we're trying to do with a neural network, actually. So let me just drag this over. All right, so let's start with the basics here. What are we trying to do when we actually solve a neural network? Well, the whole purpose of solving a neural network is we want to minimize something called a loss function. So when I look at my actuals, and I have my y actuals, and then I have my y predicted. In the previous tutorial, what we walk through is we walk through something called the random root mean square error. And this would be considered a loss function. And what it's basically saying is that for every single prediction that I'm making versus the actual, how much am I actually losing out in a real prediction? So what is that gap? What is that distance? What does that number look like? And what we're trying to do with this loss function is we are literally trying to minimize it. All right, so the whole purpose is we want to minimize the loss function. All right, so now we're going to build a simple little algorithm. So let's say we build a model. All right, so we're going to build a simple linear regression model, and we're going to say y is equal to w1 x1 plus b. So that's the same thing as saying y is equal to mx plus b. We just use w in neural networks to assign a weight to this. And so if I go ahead and I just expand this a little bit further and I say y is equal to, and I'm going to add two variables, x1 plus w2 x2 plus b. Now with a neural network, what you're trying to do is I'm going to go ahead and say I'm going to feed in my x1 and my x2 values into this neural network. So it's going to feed into this. And what it's essentially trying to do is it's trying to calculate the weight associated. Well, let's just get rid of this one. It's going to try to calculate the weight associated with W1 and W2 so that your Y minus your Y prediction is as closest to 0. Because what it's trying to do is it's trying to say, I want to make sure that I calculate the correct W1 and the W2s, the weightage for X1 and X2, so that inherently I minimize my error. I want to make sure that my error is as closest to 0. And if my error is close to 0, or if my error is 0, let's say your error is equal to 0, then Y is equal to Y predicted. In which case, that's what you're trying to do, is you're trying to minimize your error. And so as we build this neural network, and so we're going to start with our initial weights for W1 and W2. And I can go in and I can put whatever number of incoming layers I want in this. And what it's going to do is it's going to go ahead and test this neural network. So let me just draw a couple of more lines here. So if I go in with an original weight of 0.5 and 0.5, and I have a whole bunch of other hidden layers here, it's basically going to keep going until it gets to the output layer. And at the point when it gets to the output layer, it's going to make a prediction. And it's going to say, all right, my prediction for Y is equal to 100. And then it's going to say, well, and that's Y predict. It's going to say, well, what was Y actual? Well, Y actual was only equal to 85. All right, so then what it's going to say is, wait a minute, I'm off by 15. That's not good enough. I need to go backwards now, all the way back. So I need to go backwards to this layer, to this layer, to this layer, all the way back to the front and reset these weights to something else. So why don't I try 0.6 and then try 0.4? And it's going to keep going back and forth, back and forth, back and forth, until it's reached a couple of limits. So first of all, When this actually goes in one direction moving forward, this is called forward propagation. And you'll actually see that there's some models that are just forward propagation only. And when it does its estimation and realizes it's not right, it's going to go backwards, and this is called backward propagation. And so when it does one full cycle of forward and back, that is called an epoch. I think that's how they pronounce it. And you're going to see me use this epoch later on. And it's going to keep going back and forth until it actually hits my desired limit. So let's say I want this to do 50 epochs. It's going to go back and forth and recalculate this until either it hits something called the local minimum, which we'll walk through in a second, or until it actually hits the number of epochs. And then it's going to return back the result that you want. And so what it's trying to do is it's trying to find the local minimum. Now in reality, you're really not going to have a line that's as simple as saying y is equal to mx plus b. You may have something like a quadratic function, which is something like y is equal to ax squared plus bx plus c. And that's called a quadratic function when you have a order higher than just 1. And when you look at the curve for a simple quadratic function, it's actually going to look like a parabola, like this. And what it's trying to do when it's actually doing a neural network is it's taking the slope at every single point here. All right. So what it's going to do is it's going to say, let's say it starts off over here and it says this is where y is sitting. Well, if you look at the slope, that's the rise over the run. That's going to be some number, we'll call it z for now. But what the quadratic function really needs to is it needs to get to a slope as close as 0 as possible. And that is basically your error function. Because your derivative of this function here is going to be your slope of the curve. You're trying to get as close as possible to a slope of 0. Now, how do you do that? So let's say this is your starting function. How do you actually finally make your way down here? Well, when we use something called an optimizer, in this case, we're going to use, we'll use Atom actually. It has something called a learning rate. I won't go through the calculation in detail today, but I'll give you the concept. What a learning rate is going to do is it's going to go back and retest itself in small fractions as it goes down. Now, this is called gradient descent. And what it's doing is it's going down the gradient because it wants to try to find a slope as close as possible to 0. And it's going to keep doing that. So it's actually going to jump an increment of 0.01 or whatever you set the learning rate to. It's not going to be that specific number. I'm just, we're saying if the learning rate is 0.01, it's going to be some drop that it's going to go. And it's going to keep dropping. And it's going to keep looking at the derivative of the line to see how close it is to 0. Now, if I set my learning rate too high, what's going to happen in this case, let me just redraw this here. What's going to happen in this case is if I set my learning rate too high, it's going to go too far down here, and then it actually may start going the other way. So if I set my learning rate, for example, equal to, and I'm making this up here, 0.9 or something like that, it may actually go, the step that it takes down, it may be too drastic, and it may actually give you a number that's not good. And so when it takes its step back up, it's going to go somewhere up here. Its next step is going to be over here. Its next step is going to be over here. On the contrary, if you set your learning rate too low, you actually may be at a scenario where you actually never get anywhere close down here. And so it may just keep looking at the derivative here, then it'll go here, then it'll go here, then it'll go here. And by that point in time, you've actually reached your epochs. Now, one may say, well, why don't I just let my epochs run really long and set my learning rate really low? Well, you can't do that, but computationally, that's going to be very expensive. And what that means is it's literally going to take a really long time for you to run that. It's going to take hours sometimes, depending on the type of data set you have. And when you're working in data science, you need some of these numbers fairly quickly. So really, you got to find the fine balance between your learning rate, the epochs, and a few other hyperparameters that you would look at. So knowing what we know now, we know what epochs are, and that's basically your forward and back propagation cycles. We know your learning rate. It's also called your step function. It's going to see how quickly it goes down the gradient. And then the last thing I want to leave you with is, in reality, whenever you build a model, and it's a complicated model, you're never going to have a simple parabola like this. Your model is actually going to be something like this in reality. It's going to be all over the map. And when it's trying to go ahead and actually figure this out, this here is called a local minimum, because for this specific curve, this is the minimum point. But when you're actually looking for the true minimum, that's sitting somewhere over here. And in reality, you may never actually hit the true minimum, but that's okay because you're fairly close from a prediction standpoint anyways, even if you hit a local minimum. If you really fine-tune your epochs and you fine-tune your learning rate, there's other hyperparameters you can set as well, but that's more for advanced users. then you will be very close to actually getting to your minimum here, your actual minimum. So knowing what we know, let's go back to the screen and let me show you what we've built. All right, we've built a model. The model is going to be sequential, and all that means is this is going to come one after the other. All right. So what we're saying here is we're actually going to start with 250 nodes to start with. Even though I've got, call it 15, 20 different training dimensions that I'm putting in here, I'm still going to parse this out into 250 different nodes. And then as I do that, I'm going to say, all right, you know what? Take that up to now 600. Now I really want to take this fine tune. And this is where some of the science comes into this. It's really about tweaking some of these numbers. I haven't really found an effective way to automate this yet. But this is really about tweaking these numbers to say, well, what's going to get you the best overall number? And so after that, we do something called a dropout. Now a dropout, like I said, this isn't very well optimized. This is only for me to introduce the concepts to you. So what a dropout basically does, so when I have my nodes here, let's say I've got, this is my original activation layer, and then I've got a whole bunch of different nodes over here. A dropout is a type of regulator, or it's a type of regulation strategy. What dropout does is when I actually set a dropout rate, let's say I set it to 0.5, what it's going to do is when this is actually doing my forward propagation, it's going to randomly go ahead and look at all of these different nodes, and it's going to turn off, and I'm going to add a sixth one just to make this easy. It's going to go ahead and turn off 50% of these. So these are no longer accessible in this iteration that it's going to do. And so really now this has got to work with 3 nodes in this scenario. And so the next time this comes around, let's say it does another epic, it may turn off a different 3. The whole purpose of that is you want to try minimizing overfitting the model so that it works for your training set, but it never works for your test set. So a dropout is a type of a regulation function, if you will, that will help you with minimizing your overfitting. And picking the right dropout rate, as well as the number of dropout nodes to add in, is again a little bit of a art versus science in this case. But I've added this in just to show you how this works. And then I said, all right, let's go ahead and put this through 500 nodes again twice. 2 more times, and then finally let's predict that y and see what it's going to be. Now Adam comes with a default learning rate which is 0.01, so I've left it at that. I haven't touched it. The loss that we're going to be minimizing in this case is mean squared error. However, remember we were looking at root mean squared error above. You'll see down here when I actually do this, I do take the square root of that number when we actually try to print it out. The optimizer we're using in this case is Adam, which is what I've identified, and I wanted to print some metrics for me. So mean squared error metrics. And so what I've done here is I've defined my data frame, and I said y again is equal to price. Now this price, because I haven't touched anything, is already filtered out for plus or minus 2%. I haven't really fiddled with that, so that is still in check. I'm still using the columns that we selected above to make this an apples and apples comparison. And that is the ones that we picked from our random forest model. And then finally, I create a test and train split set. So 25% of my set is going to be retained for test. So this time around, I did go ahead and scale the data. So I used a feature called min-max scaler, which is available in, I believe I added it all the way up here. A min-max scaler is available in sklearn.preprocessing. And so basically it's normalizing my data and it's putting it between 0 and 1. And then finally, I did the same thing with my test set so that I can do that. This is going to go ahead and make the prediction. So my X train, my Y train, I've set this to 150 epochs. Now I've set the batch size. Because this has like 4,500 rows, it doesn't make sense to take the entire data set every time. So I said, let's do batches of 40. And you can tinker with this number as much as you want. You can take this to 100, 200, 300. You can use the entire data set if you want, but I found this to be effective. You can set shuffle equal to true, but I just turned it off. Now verbose here, I set this equal to 0 because I don't want to see all the different modeling run down here. What I'll do is I'll set this epic down to like 10 and I'll show you what you see with verbose 1 and 2. And then you go ahead and print out the model. So let's see what this predicts. And as you can see, this has a few lines of code to build a neural network. It's actually not very tough to build, but let's go ahead and see what this predicts. And remember, this is going to take a little bit of time because it's going through 150 forward and back propagations. And it's pulling random batch sizes of 40. But we're going to hopefully see very soon what number this spits out. And when it is testing this, remember this is doing it against a test set here. So we're going to get a true representation and see how accurate this is. Alright, so it came out with 98,694, which is actually not too far off from Random Forest, which is 95,437. And it still did do better than all the other ones. Now remember, the Random Forest one I did tweak a little bit. This one is literally out of the box. I haven't done any tweaking to this. I bet you if I tweak this, I could probably bring this down by about at least $10,000, maybe a little bit more than that. But I'd have to play around with some of these metrics. So I'm going to show you one more thing, and now that is if I change this to, let's say, 10 epochs, and I'm going to put this verbose equal to 1 so that you see actually how this is calculating in the background. And you're going to get a completely different number because I'm tweaking this around, but let's run this. What you're going to see is now it's actually going through all the different epochs. It's going through the first one, the second one, and as it's going down there, this is now, remember, printing out the mean square average. It's not the root. We have to take the square root of this still. But it went ahead and it printed all this stuff out, and now the number is a lot higher. It's $111,000 or so. But it will literally go through every single one of these epochs. It'll say, okay, in this specific epoch with this batch size of 40, I actually achieved a mean square error of this. And it'll go all the way down and look at, different numbers as it goes down this path. And so this is giving you one view of it. If I go ahead and turn this to verbose equals to 2, it gives you some detail, just not as much. And in this case, it's just calculating your loss for you. It's not giving you all those fancy charts. This time you get 109,423. Alright, this was just a quick introduction in solving a problem that we've solved already using different methods, but this time building a neural network from absolute scratch. Now, like I said, I like building neural networks when it comes more for classification models, so we will be building something like that in the coming future. However, for today, I just wanted to leave you with this. I know neural networks sometimes are a little bit complicated to digest. Some people find these a little bit intimidating to use, but I can tell you they're actually very straightforward to use. And as you start reading some of the documentation, especially for TensorFlow, now I'm still using TensorFlow 1.9 or 8 or something like that. TensorFlow 2 is out and it's apparently supposed to be a lot better. I've yet to play around with it. But hopefully you enjoyed this video, guys. And again, if you like this video, please like, subscribe, and comment and share. Remember, I'm putting this stuff out for free. People are charging tons of money for this. So if you agree with me, hit that like button, hit that subscribe button, and I'll talk to you next time. Thanks very much.